Alright, so first off, you have Democritus, Dalton, Thomson, Rutherford, Bohr, and present model. Okay, so this is a particle that can't be cut anymore because it is too small. This is discovered by Dalton, saying that all matter is made of atoms. All atoms of a given element are identical in mass and properties. Compounds are from two or more different atoms. Chemicals, reaction, rearranges atoms, and atoms are neither created nor destroyed. This one is by Thomson. Negatively charged ions in a positive ion. So Thomson discovered this by experimenting with plum pudding and calculating the mass of the rays. Next, we have Rutherford. Atoms have a lot of space, positive charges, and are centered. He did this by doing gold foil experiment. From shining light to gold foil, it bounced around, boom, 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 all around in different directions. So he concluded that atoms have a lot of space. Bohr, you can think about as Bohr ring, because he discovered the rings. So the description is: electrons orbit the nucleus without losing energy. Low energy electrons orbit closer to the nucleus, and they only move in fixed orbits of specific energy, is Bohr. Present day model. Electrons have such high energy they won't follow specific paths, and they did this through the quantum mechanical model to understand the place of an electron. Alright, those are the atoms. On to next, isotopes. So isotopes. An isotope is the same element, however, it is different. Alright, so let's do an example. Cl 17. That is chlorine, which, holy guacamole, chlorine has a mass 35.453. 35.453. This number is not always the same. So the amount of protons and electrons and then neutrons. So protons obviously is the atomic number, so 17. Electrons are neutrally the same as the protons, or if they're neutral, it's the same. So, in order to get the neutrons, we do mass minus the protons, so 18. So now using this, we can fill out this table. So atomic number 1, that is hydrogen. Amount of protons, these atomic number and protons always the same. So 1, the mass is 1. So therefore, if mass is the combination of protons and neutrons, then the neutrons would be 0, electrons 1. I hope this makes sense. Symbol nitrogen. Given that there are 8 neutrons, 7 protons, that would be 15 mass, and 7. Let's fill out the electrons and the proton list for now. This mass of 2. 5, 10, 126, 53, 53, and then this is I, H, and then PB. So, yeah. However, let's look at number 1, number 5. These two are an isotope. Why? Because, go back to the definition, an isotope is same element, different mass. Look right here, mass 1, mass 2, boom, that's an isotope. Okay, so moving on, let's calculate the isotope of copper 63 and copper 64. Well, as you can see, using the periodic table, copper is around this mass, atomic number 29. So mass 63, mass is 64 here, minus the atomic number, which would equal 34. And this one 35. Moving on, how many neutrons in the isotopes of carbon? So 12, 6C, 13, 6C, 14, 6C. These are the protons. This is the mass right here. So mass minus the protons is how you get the isotope. So 6, 7, and 8. Alright, next up, we are calculating the average atomic mass. Let's see, if you have O16, O17, and O18. O16, it is given that it is 99.76. This is 0.04%. This is 0.02%. So, how would you do this? Well, you would do 16 AMU, 17 and 18 AMU, and then the multiplied by the percentage of 4.2. This should equal 16.0044 AMU. Let's do another example. ZN64, ZN66, ZN67, ZN68, and ZN70. This is 0.6%, 18.6%, 4.1%, 27.8%, 48.9%. These values are given. So this is a bit tedious, but 64, 66, 67, 68, and 70. Actually, disregard my work right here. This should be 9.76 moved to decimal, because you're trying to convert percent into an actual number to multiply this .0004 and 002. Alright. So, sorry about that, but 1, 2, 3, 4, 1, 2, 3, 4. Alright, so 0.006. 0.041, 0.278, and 0.4. This all would equal 65.459. Okay. Like the previous table, let's do atomic number, mass number, protons, electrons, neutrons, then charge. If you're given, oh, what is this? Okay. Symbol. So if you're given 46, 38, and 40, that would mean this is 40. This number is 86. And that would mean the charge is +2. I did not give enough space. However, this would be 86, 40, CR, 2 plus. Goal minus does not care. If the plus right here is in the front, so it could play +2 CR or like 2 plus CR. Yeah, goal minus does not care. I don't know about Willis or yeah. Another example, 92, 38, 86. Then this is 152, 92. This would be +6. You are wondering how I am getting the charge. I am getting the charge by doing the amount of protons minus the electrons. So 40 minus 38 is +2. 92 minus 86 is +6. Let's give an example where it's negative. So 34, 36, 45, 79, 34, +4. So just in case you forgot how to do the symbols, symbol is 92 for this one because the protons, the mass is 238, and the atomic number is U, so +6, because the charge goes to the top right. Let's start with the charge here. SE. This is 79. Alright. So typically you would want to draw the electrons in pairs, but you don't really have to. Next is, I would say, very important that most people probably forget about. This so let's see. Okay, so very important to know that the Coulombic attraction the ionization energy and electronegativity. They all get larger as they go to the upper right. However, the radius of the atom gets larger when it's going that way. So if here, let's say this one is like down there, yeah, the radius is the only one that gets smaller. Next, this is probably going to be on some FRQ. Let's get the electron configuration. I'm not writing all that. Of, let's say, nitrogen. So, nitrogen is right here. So, how you get the electron configuration, start from here, 1s, boom. You're reading it like a book, from top left to right, 1s, 2s, 2p, here is nitrogen. So 1s, 1, 2. So 1s2, 2s, 1, 2, 2s2, and then 2p, 1, 2, 3. So the electron configuration equation is 1s2, 2s2, and 2p3. You're probably gonna be required to draw a diagram like a skibbity sigma. Oh no. Actually, I don't even need to draw this much boxes. So this is 2p, 2s, 1s. So how you do this, if you forgot, each one box right here represents like half an arrow or something. So since there's like 2 boxes, 1, 2, 4, so 1, 2, 3, 4, boom. Then each box has to be filled out before you do another side. So boom, you can't do this. You have to fill out the whole row before you do that. So that is electron configuration, if you forgot. Oh, if you want to do the noble gas shorthand, that would be helium because it is the closest back. You can't move forward when doing the noble gas shorthand. So it is helium right here, and then you can just skip this, like boom, boom, just write 2p3. Let's do another one of here. This one is long. Fe plus 3. So Fe is, oh my god, if I can find it, Fe, oh, it's iron, I forgot. Oh, my bad. Oh no. Alright, so this one is going to take a while. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and the transition metals, they are basically always one number behind the S after it. So it is 3D. 1, 2, 3, 4, 5, 6, 3D6. The noble gas. Shorthand would be argon. Do 4s2 3d6. Oh wait. I think I accidentally skipped 2s2. So, writing the orbital diagram for this is square, 1, 2, 3, square. Wait. So 1, 2, that's 1s, 2s, 2p, 3s, 3p, 3d, 4s. Boom, 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 boom. You can just fill this out because you don't need to worry about this yet until you get to this. So 1, 2, 3, 4, 5, because to put each on one side. Then you can just go back to that first box, and yeah. Next step is the wavelength. So wavelength gets gradually bigger. So the energy increases from right to left. The wavelength increases from left to right, and the frequency is right to left. I don't think knowing the colors for wavelength is like too important, but like let's see, as the wavelength increases, so red, this is violet. I'm pretty sure that these two are the main ones you need to know. But just in case, I'll just do orange, yellow, yellow, green, green, blue, green, blue, and violet. So I think that is it, unless fine. So let's say that you are given hydrogen, let's just call this A, B, C. So pretend these are like real elements. I didn't feel like thinking. So let's see. If you're unknown X and unknown Y, alright, so it's unknown X, unknown Y, pretend these are elements. So unknown X would be this one, and this one. Unknown Y would be B and C. Oh wait, no, B and H. B, H, and then C, and B. Alright, I'm so done with this, bro.